There's a scandalous star you've probably seen in the night sky. It's called Betelgeuse, situated in the Orion group of stars, denoting Orion's right shoulder. However, this star's behavior lately has been unusual. This red supergiant has been darkening habitually throughout the course of recent years, which could demonstrate that it's very nearly going cosmic explosion. The distance between Betelgeuse and Earth is about 600 light-years, which means that the star produced the light we see today about 600 years ago. Strangely, we don't have a clue about its precise distance, yet it's in that ballpark. On the off chance that Betelgeuse had proactively detonated in a cosmic explosion inside the most recent 600 years, the light from that blast would in any case go toward us. As such, it's conceivable that Betelgeuse has proactively detonated hundreds of years prior, and we could see the blast out of the blue, even tomorrow. Betelgeuse's supernova will be the brightest ever observed by humans when it does occur. All in all, exactly how splendid will it be? Will it be apparent throughout the day? Will it represent any risk? Also, for what reason do ongoing perceptions of Betelgeuse challenge our ongoing comprehension of heavenly material science? Hydrogen and helium, the lightest elements in the universe, make up the majority of stars, including Betelgeuse. At the point when the center runs out of atomic fuel to melt, it can never again uphold the star's external layers, prompting a gravitational breakdown. As the star implodes under its own gravity, it warms up and packs until the tension turns out to be excessively perfect. This fast breakdown produces a shockwave that brushes off the star's external layers in a huge blast. A supernova is the result, and it gives off a lot of energy and light, sometimes shining brighter than entire galaxies for a while. To put this into perspective, our Sun has a luminosity of 3.8 × 10⁻⁶ watts, or power output. In any case, a cosmic explosion saw in 2015, called Assassin 15 LH, arrived at a pinnacle glow of around 2 × 10⁻³ watts. The brilliance would be the consolidated result of north of 500 billion suns. You ask, why didn't we see it from Earth? All things considered, Assassin 15 LH was situated in another universe. Betelgeuse, nonetheless, is in our grandiose terrace. This nearness implies Betelgeuse's cosmic explosion would be amazingly brilliant, possibly eclipsing even Sirius, the most splendid star in our night sky, and it would probably stay apparent for a really long time. In any case, will it represent any risk to Earth? A supernova that explodes within a few tens of light-years of Earth would have serious repercussions, including the exposure to harmful radiation. The peril zone for these impacts is assessed to associate with 100 light-years. Luckily, Betelgeuse is past this reach, so we are secure in general. As a point of comparison, if a nearby star like Alpha Centauri, which is just over 4 light-years away, went supernova, it would be as bright as the moon and emit harmful radiation that could harm Earth. Be that as it may, Alpha Centauri isn't sufficiently gigantic to turn into a cosmic explosion. Betelgeuse is currently the most intriguing of the visible red giants that have the potential to go supernova, and its recent activity has sparked concern among scientists. Betelgeuse's rotation is one of its fascinating characteristics. Betelgeuse rotates about once every 20 years, which is surprisingly fast for a star of its size, according to recent observations made with the ALMA array of telescopes. This implies its surface twists at about 18,000 kilometers each hour or 5 kilometers each second, a lot quicker than Earth's revolution. This quick revolution is surprising for a particularly monstrous star and difficulties how we might interpret heavenly physical science. In any case, how would you gauge the turn of an enormous body so distant? We utilize the Doppler impact. Envision an emergency vehicle with its alarm blasting, moving toward you. As it draws nearer, the alarm appears to be higher in pitch. As the ambulance approaches you, the sound waves are compressed, causing this. The sound waves are stretched out as the ambulance moves away, making the pitch appear lower. The Doppler shift refers to this movement-induced pitch shift. Similar to Betelgeuse, a gradient of color shifts can be seen as one half of the star's surface moves toward us and the other half moves away. Scientists are able to ascertain the star's rotational speed by observing these shifts. This speed was found to be much higher than expected for Betelgeuse, leading researchers to speculate that it may be caused by a massive cosmic phenomenon. One hypothesis to make sense of this peculiarity is heavenly savagery, where Betelgeuse could have retained a friend star, picking up extra precise speed all the while. Betelgeuse contains undeniably more nitrogen in its external air, which is an indication that its inside has been blended as of late, demonstrating that something happened to the star to turn it up. Assembling these pieces, cosmologists as of late played out an efficient and cautious investigation of the interesting chance that Betelgeuse didn't get going as a solitary star, however, is rather the result of a crash. The companion star's orbit was covered by the supergiant star's atmosphere as it got older. Researchers played out a reenactment that uncovered the buddy star's gravity piped that material onto itself, expanding its own mass. In the end, the sidekick began swimming through such a lot of material that this caused rubbing, easing back the buddy and drawing it internal. What occurred next relied upon various elements, including the speed of the sidekick, the star's relative masses, and the amount of the essential star's air had been expanded. The convergence of new material from the buddy star disturbed the helium center, momentarily returning the recently blended star to a hydrogen-centered melding stage. Reproductions show, nonetheless, that this didn't keep going long, and the infant Betelgeuse before long turned into a red supergiant once more. Tragically, direct proof for this situation will not be quickly clear until Betelgeuse detonates into a cosmic explosion. Another possibility is that the star's turbulent surface causes the observed rotational speed to appear as an optical illusion. Late perceptions utilizing progressed telescopes have uncovered that Betelgeuse's surface isn't smooth but instead rising with extreme action. These surface air pockets are really gigantic convective cells, districts of the star where hot plasma rises and cooler plasma sinks, making a dynamic, irritating surface. The foaming, or convective movement, on Betelgeuse's surface causes varieties in temperature and splendor. These varieties make shifts in the shade of the light transmitted from various pieces of the star. Basically, depending on whether the star's surface is moving toward us or away from us, its turbulent motions can make certain areas of the star appear redder or bluer. Astronomers may have been deceived by the convective cell's color gradient into thinking the star was rotating at a faster rate than it actually is. Scientists can deduce the star's rotational speed from these changes in color and brightness. To more readily comprehend whether this gurgling is to be sure making the noticed variety slope, or then again assuming there are different clarifications, cosmologists are zeroing in on getting higher goal pictures and more point-by-point information.